Let's talk about bonding and hybrids, and this is going to be important to your passing the AP test. What's the empirical hurdle that all bonding theories have to leap? Well, it's got to predict the right bond angles. And the question is, can molecular orbital theory, overlapping atomic orbitals, can that do it? It's got to predict 109.5 degrees in things like methane, 120 degrees in the trigonal planar molecules, and 180 degrees in linear molecules like carbon dioxide and beryllium fluoride. It also needs to predict the trigonal bipyramidal and octahedral geometries. Now, Vesper tells us that the number of electron centers and the repulsion between them helps us to figure out what the molecular geometry is. But again, the molecular orbital theory math also has to work. Now, a normal sigma bond is the overlap of two atomic orbitals. There's a bonding orbital. That's the sum of complementary orbitals. Those are the orbitals on the two atoms that if you add them together, it gives a low energy molecular orbital. There's also an antibonding orbital that is the sum of non-complementary orbitals. Those are the orbitals functions that when added together gives you a high energy. The antibonding orbital in stable molecules is empty because the stable molecule has its electrons in the ground state. Now, the highest electron density in a chemical bond is right between the two nuclei. We remember what the interatomic distance is. It's the distance at which the attraction offsets the repulsion between the two atoms. If the nuclei are too close, you get net repulsion. If they're too far apart, you'll get net attraction. What that leads to is a vibratory mode. Bonds act like coiled springs, and the atoms will move together and apart around the covalent bond. So how do we explain these bond angles we observe in nature? Well, let's talk first of all about beryllium difluoride or beryllium fluoride. If we heat the solid in a flask, it turns directly into a gas. If we then take the gas and run it through a spectroscope, we see the characteristics of a linear molecule. That is, the bond angles are 180 degrees. Vesper, of course, predicts that with two electron centers, you will have a linear molecule. But wait a minute. What is a beryllium electron configuration? Well, we know it's 1s2, 2s2. And if we graph that out in boxes, we see all three p orbitals are empty. We've got a full s orbital on the second and first energy level. How do we get two bonding orbitals out of this? Well, the solution is that beryllium, of course, does form covalent bonds with two fluorines, so we have to admit that reality. Now, not the full s orbital and not the p orbital. The bond lengths have to be the same. Spectroscopes tell us that the bond lengths are the same, not two different bond lengths. So what we do is we promote one of the electrons to a p orbital, and then we hybridize the half-filled s and the half-filled p orbital to form two orbitals. They're called hybrid orbitals. See, so we'll move that together. So now we've got two of the 2sp hybridized orbitals and two of the 2p orbitals remain, and they are empty. Hybridization was, of course, the idea of Dr. Pauling. Now, what is the electron density or distribution of these hybrid bonding orbitals? Well, we can get this from the Schrödinger math. And we put that in the graphing equation, and we remember that the p orbital has a node running right through the nucleus. So the sp orbital should also have a node. The p orbital has a linear orientation. Symmetry is around an axis, x, y, or z. So the sp orbital should have a linear orientation. Now if we then do the Schrödinger math, mixing the s and the p electron distributions, the two psi functions, we see an asymptote, a node running right through the nucleus. That's an area where there's zero probability of finding the electron. This is one of the two sp orbitals. It has a linear orientation as well. Now we can use the software and rotate the orbital. You can see the axis moving here. And we find that from the Schrödinger math, we can also get a lopsided distribution. Remember, the psi function on the p orbital, on the left and the right side, they're opposite in sign. One is plus, one is minus. When you square it to get the probability distribution psi squared, of course, all the negatives turn positive. Remember, we add the psi functions, not the psi squareds. So the s orbital is always positive. Now when the s is added to the p, the negative lobe partially cancels or destructively interferes with the positive s electron. And that's what gives this lopsided distribution. Something similar happens when the functions are subtracted. That's the other root of the Schrödinger equation here. And the opposite occurs. When the s orbital bonds, then, there is little electron density on the off side. On the on side, the electron density is very high. And of course, then the bond is going to occur there. Now, how do we explain trigonal planar molecular geometry, for instance, in the BF3 molecule? Well, that has 120-degree bond angles. Vesper predicts that. Here we can use what we call sp2 hybridization. We take the boron, we promote an s electron to one of the p orbitals, and we move them together, hybridizing them, mixing them up, if you will, and we leave a 2p orbital unoccupied. We now have 3 sp2 orbitals. If we graph these, we see that the atomic orbitals are orthogonal, that is, they're perpendicular to each other in the same plane. Now, how do we explain a tetrahedral molecular geometry? For example, methane derivatives like carbon tetrachloride, CCl3, are forming a tetrahedral shape. Well, we've still got a p orbital left, and remember, carbon is 1s2, 2s2, 2p2. So if we promote that s electron to that third p orbital, and then hybridize all 4 of the orbitals, we get 4 hybridized orbitals, which we name sp3 orbitals because they're the mixture of 1s and 3 p's. There are 4 equivalent orbitals now that we can overlap with chlorine or hydrogen or anything else, and we'll still have that tetrahedral shape. The math gives us a tetrahedral geometry when we combine the Schrödinger wave function psi for these to give the 4 orbitals. The electron geometry then is tetrahedral. Now, let's look at nitrogen compounds. If we postulate sp3 hybridization again, all we need to do is recognize that there is one filled orbital, the 2s orbital. So when we hybridize, we now have 4 sp3 orbitals, but one of them is filled with electrons, as you see in the box and the orbital diagram. This unbonded pair now constitutes an electron center with nothing attached to it, which means that it is free to push a little harder on the other orbitals, and it widens the upper bond angle, reducing these bond angles to 107 degrees. What about oxygen? Oxygen has 2 electrons more than carbon. In the 2s2 and the 2p2, the 2p orbitals, we have 2 electrons in the x, 2px2, and then 2py1 and 2pz1. If we hybridize, we now have again 4 sp3 orbitals, but 2 of them are filled with electrons, as you can see in the diagrams here. The 2 unbonded pairs now are going to push on the bonded pairs and reduce the bond angle between the, for instance, hydrogens and oxygen even further to 104.5 degrees, which is what we see from spectroscopy. This gives us our quantum picture of water, and of course it means that water is a polar molecule. We can now see the hydrogens attached and the 2 unbonded pairs or lone pairs pushing on those hydrogens to give us that characteristic 104.5 bond angle. What have we explained so far? Well, we've explained linear molecules with sp hybridization, for instance in carbon dioxide or beryllium fluoride. We've explained the trigonal planar geometry using the sp2 hybrid overlap, for instance in boron trifluoride or boron fluoride, 120 degrees. We've explained the tetrahedral configuration with the sp3 hybrid, and orbital overlaps will give us the 109.5 degrees. We've explained methane, we've explained why ammonia has a smaller bond angle, and why water has an even smaller bond angle than ammonia. Now, we can also, when we get to higher energy levels, third energy and so forth, we now have access to the d orbitals, and we can explain other hybrids. Hybrids can form between sp and d orbitals. We can involve either one d orbital or 2 of them. If we involve one d orbital, we will form a trigonal bipyramidal structure. sp3d hybrid is what is postulated here. And if we involve 2 d orbitals, we'll form an octahedral structure. And the physical chemists call this an sp3d2 hybrid. However, this is not 100% accepted in quantum chemistry circles, and the good news is it will not be tested either by me or by the AP. Always remember, the number of hybrid orbitals is exactly the same as the number of unhybridized orbitals used to make them. So don't lose any. So if you have 1s and 3p orbitals, you'll get 4 sp3 orbitals. If you have 1s, 3p, and 1d orbital, it'll make 5 sp3d orbitals. Again, no test on that. So, why don't you identify the hybridizations on the following molecule? You can stop the video while you work it out. Notice here the number of bonds on the carbon, here the number of bonds on the carbon, and here the number of bonds on the oxygen. Here's the solution. You have sp3 hybridization on this carbon and on the hydroxyl oxygen. And you have sp2 hybridization here, where you have a double bond that's typical of sp2 hybridization.